Hello, it's Scott Manley here. This is an amazing view of the back of the Space Shuttle from engineering camera number 19, or Echo 19 as they say. I believe this is from 2005 and it's using 16mm film. On the right you can actually see the sprocket holes at the top and the bottom and the time code in the middle. Now, if you are a space fan, you've almost certainly seen this before. NASA released a compilation of about 40 minutes worth of this engineering camera footage, along with commentary by individuals who captured the footage and analysed the footage. And it's a fantastic video with all these angles, which I've compiled here into one so you can get an idea of the magnificent sequencing of events that goes on during a shuttle launch. But I actually wanted to use this footage to go into a few more details that they didn't cover and specifically talk about the exact moment-by-moment sequence of events that has to go into making a space shuttle launch. And while the space shuttle stopped flying 10 years ago, this is all still very relevant because SLS is going to use the same rocket engines. It's going to use practically the same booster design. It's very likely going to use similar hardware and similar sequencing, and that is going to happen in a few months from now. Fingers crossed. And I really hope that we get footage of this quality from the SLS launch because this is first-rate rocket porn. Now, a couple of years ago, I did this video about how the F1 engine on the Saturn V starts up, and that is a vastly simpler engine. The Saturn V engine is an open-cycle engine that powers its pumps with a gas generator that basically blows hot gas over a turbine, and that gas is then dumped overboard. But on the Space Shuttle main engine, that is a closed-cycle engine where the output from the gas generator is fed into the main combustion chamber, and that means that the downstream pressure from the turbines is higher, and they have to be very careful during startup that the pressure in the combustion chamber never gets high enough that it blows and flows backwards through the system, stalling the startup. The F1 engine started up as a series of small discrete events which were sort of triggered when pressure thresholds were met. The Space Shuttle main engines have a computer that is very carefully controlling all the valve positions and reading out sensors to make sure things happen exactly in order. And if you look at the valve positions over time, this is a very complicated startup experience. And I'm told that at every point of inflection, every time they change a valve position, that is because of something they learned during testing. And there is very likely a destroyed husk of an engine somewhere that showed them that they needed to change. One source stated that it took 38 tests over several months just to get through the full startup sequence. And during this, they had to replace the turbopump assembly 12 times. The full Space Shuttle countdown actually starts like 72 hours before the launch. Propellant loading starts about 6 hours before that. Crew gets on at 3. The crew access arm is retracted at about 7.5 minutes. At 3 minutes 55 before launch, they perform a test of the aerosurfaces to make sure they're performing. You can also see condensation plumes from helium and nitrogen that are being pushed through the engine to make sure that there's nothing in the engine that will freeze when the propellants are introduced. They need helium because liquid hydrogen will cause air to freeze solid. Now they're testing the engine gimbals. They move it through a set of pre-arranged motions, and once they finish this test, they will spread the engines out into the launch configuration, making sure that the engine bells are as far away from each other as possible so that when they wobble around during startup, they don't hit each other. 2 minutes and 50 seconds before launch, they retract the gaseous oxygen vent arm, also known as the beanie cap. This captured oxygen that was vaporizing inside the propellant tank and made sure that it didn't cause ice to form on the top of the tank. Now we're down to 10 seconds before the launch. The first things that light up are the ROFIs, the radially outward firing igniters. These are throwing little hot pieces of burning metal into the air, and their task is to find any hydrogen and make it burn so that it doesn't build up and cause a big explosion. The ROFIs are single-use devices. If they have an abort after this, then they have to call a scrub for the day and have the ROFIs replaced. They light up about 3 seconds before the engines actually start, and because this is super slow motion, we can point out a couple of extra things here. You can see the AJ-10 orbital maneuvering system engines, and you can see the cluster of reaction control thrusters, and you'll notice that these have covers to stop the local wildlife from making nests in them. Engine ignition starts at T-minus 6.6 seconds, and to walk through this, I'm going to cut the speed in half and use this very nice graph I showed you earlier. The main things to watch are the blue line which is rising right now, that is the main fuel valve, and the dotted magenta line which has just started rising, that is the main oxidizer valve. So the hydrogen starts flowing into the engine, but the engine is warmer than the boiling point of hydrogen, so it vaporizes. And that, on one hand, helps provide pressure to spin up the turbines, but on the other hand, the back pressure actually causes pressure waves or oscillations in the propellant flow. And these are significant enough for the first second and a half, they actually have to time some of the valve position adjustments to line up with the oscillations. Now, if you look on the left, you can see now that there is fire, and that's because there's hydrogen coming through the engine, but there's not much in the way of oxygen just yet. But that's going to change very quickly as the oxygen flows through the system, even at 60% open valve position. So the next thing that's happening is they're closing the coolant control valve a little, and that reduces the amount of hydrogen being directed to cool down the engine, and that forces more hydrogen into the combustion chamber at the same time as the oxygen arrives. So that's how we're suddenly getting these blasts as the pressure is building up in the combustion chamber. Now, up to this point, it's all been operating in open loop control, which means it's pre-scripted, but now the computer's switching over to closed loop where it starts reading the sensors and reacting. The oxygen valve is also starting to open, and the pressure inside the combustion chambers is going to start rising. We're going to transition away from this red, low pressure flame to the blue exhaust that we know on the Space Shuttle. And at this point, you want to start watching those nozzles very carefully. You're going to see them wobble. And you can also see a blue shock pattern forming on the inside. This is the flow separation layer. The gas pressure is below atmospheric pressure, so the air is pushing up inside. But as the pressure from the exhaust gets higher, it pushes this further and further down until it's eventually sitting on the very tip of the nozzle. And the moment that happens is when you get the classic shock diamonds forming. This is now about 3 seconds before launch, and at this point the onboard computer checks that all 3 engines are generating 90% thrust. If not, then it will abort the shutdown, but if so, it will be preparing to light up those solid rocket motors. And for the next couple of seconds, there's a little bit of dynamics that's kind of unique to the Space Shuttle. Because the shuttle is mounted on the side, the engines produce a torque, and if you watch the edge of that vertical racetrack on that booster, as those engines are firing, the whole stack is getting pushed to the left. You can see it very slightly moving. The top of the shuttle moves by a couple of meters, and then it begins to swing back. In technical terms, they call this twang. And when the whole thing swings back to its start position, that is the moment that the solid rocket motors will ignite. And while we wait, you can notice that the covers to the reaction control thrusters have burst due to the pressures of the ignition. But now we've twanged back and the solid rocket motors ignite. They take a fraction of a second to reach full thrust and the whole vehicle begins to rise. Now if you look very carefully on the left behind the engines, you can see the door to one of the aft service masts and it's closing down behind it. We'll see this from the other angle, I just want you to see that here. Also, look at the difference between the two different exhausts. The hydrogen exhaust is practically transparent, whereas the solid rocket motor exhaust is white hot. In fact, it's so white that the camera has adjusted its gain downwards, and the blue sky in the background now looks a dark blue. Solid rocket motors are very bright because they have a lot of particulates in the exhaust, and they're very hot, so they emit black body radiation. Hydrogen-oxygen engines have an exhaust which is mostly hot molecules, and those aren't as efficient as emitting light, so that's why the exhaust isn't nearly as bright. Now I want to rewind to t equals 0 because there's a bunch of stuff that needs to disconnect. So at the top left you have an umbilical which goes to the external tank. Below that you have one of the umbilicals which is attached to the tail service mast. And at the bottom you have the hold down posts for the solid rocket motors. The tank umbilical is there to collect hydrogen that vaporizes inside the tank, and it is connected to a large arm which swings away and pulls it away from the vehicle. The tail service masts, those two umbilicals, one is primarily for liquid hydrogen and the other is primarily for liquid oxygen. There are other connections here, but in both cases they are connected to very heavy weights, which when released pull them back inside the tail service masts so that then a set of doors can swing down to protect them against the rocket exhaust, which is about to fly by and potentially toast them. And finally, the hold down bolts. There were 4 per booster, and this was the entire structural support for the entire vehicle. And if you see that flash, that was it. That was the charge being used to separate the bolt. Now it's just sitting held down by the weight, and the engine lights and the whole thing starts to lift off. Now, you didn't see any debris flying anywhere because there is a metal cap which actually is supposed to collect or capture the debris and stop bits flying off and potentially damaging things. As you can imagine, these are some pretty big bolts. They're about 3.5 inches across, or about 9 centimeters. Considering that they needed to handle that entire twang motion that I talked about earlier, where you have 3 Space Shuttle main engines pushing the whole stack to the right. They apparently sometimes had problems with the nuts not entirely separating and hanging up, but there was enough power in those boosters to actually force them through these problems. So that is how the Space Shuttle got through the last 10 seconds before it started to move. How it spun up the engines, detected that they were running, how it ignited its boosters and then detached all sorts of hardware so the vehicle could fly free. Of course, the countdown then started counting up and it had many more actions. It had to perform the roll program. It had to adjust its throttle as it went through max Q. And of course, separate its boosters and later the external tank as it finally made its way to space. I'm Scott Manley. Fly safe.